Now, with this multi-level index, do we solve all our problems? I wish we could, but well, what if my file system doesn't have only large files, but it has a mix of few small files and few large files? What do we do then? That's one question. And also, the second thing that's still troubling me is in this approach of multi-level index, we are using significant amount of blocks, which is basically the space which we might be able to use towards storing an actual data, just to store this metadata. So let's say if there is a very big file, we are able to accommodate that accessing that big file with this approach, but then that very big file will lead to many pointers, and many pointers means much more space that's occupied by this metadata in this approach. Can you think of a idea that would help us to reduce the space that we are wasting for the metadata? So let's see that now if our file is distributed across these 5 blocks, we are storing 5 pointers for that. But rather than storing 5 pointers for a file that's distributed across 5 blocks, what if I just store the pointer to the start of that file and then the size of that file? Something like a notion that says me that, hey, this file starts at block ID 51 and size of this file is 5 blocks. So then I know that in order to access this file, I will be accessing 51, 52, 53, 54, and 55, these 5 blocks. Wouldn't that save me all this information of all this extra space that I'm wasting for this additional pointers? Now, this is a very small example, which is we are just having 5 pointers, but if the file size is really big, we could have many pointers. So then with this little idea of rather than storing pointers to all the blocks, just storing the size of that file could save us a lot of space that we are wasting for metadata, right? So let's call this as extent. What is an extent? It stores the pointer and it stores the length. The notion of length, in this case, it's the number of blocks over which this file is stored. So if we have such extents or extent-based allocation mechanism or extent-based data organization mechanism, then what we are doing is, instead of storing pointers to each data blocks of disk, now we are storing the first block and then length of the file. The advantage of this mechanism is definitely less amount of metadata. Are there any disadvantage to this mechanism? Well, by now you must have learned that every solution to a problem has new problems, right? As I have said infinite number of times till now, and that would be in your thought process iteratively already. So what is the problem here with extent-based mechanism? The biggest problem, I'm sure you already have it there, right? Is it's less flexible. Than pointer-based approach. Why it is less flexible? Well, what if there is not enough contiguous space on disk to accommodate whole file? What do we do in this scenario? If we do not have enough contiguous space on disk to accommodate this entire file, then this approach of just storing the starting address of the file and the number of blocks over which this file spans would not work, because in that case, let's say this file would take the file that we want to store might take 9 blocks, but let's say the maximum possible contiguous blocks that we have available or free on the disk currently is just 3 blocks. But we have like bits and pieces, 3 blocks here, 2 blocks after some space, then a chunk of another 3 blocks after some space, 1 block thereafter. But we do not have contiguous 9 blocks. In that case, this approach of just storing the start and the length would not work, right? So although we are able to save the space that we are wasting for metadata, but we still have a bit of unsolved problem with this approach. And if we are using such an approach, then we are left with this at the end for such a file that's ranging over 9 blocks. We would have to say to the reply to the user with saying that, sorry, there is no more space on the disk for this file, right? But the disk eventually could end up fragmented because it has this pieces of empty space, which can no longer be used. So the contiguous allocation has the problem of not being able to work if we do not have contiguous space, extent-based technique, and also it could cause fragmentation. How do we solve this? I'm sure, again, you are ringing the doorbell to your data structure repository, thinking of, well, what data structure or what mechanism could help us to solve this? Well, one of the technique that we could think of is, let's say that we know that we have 9 blocks available on the disk, but not the contiguous ones. Then we could store link or chained structure. So in the structure, each block points to the next. So rather than just storing the starting address and then the length in our extent, we can design a mechanism where we still store the starting address, but then each block, so now the first block will then point to the next block, whichever the block that consists the next segment of this file. And initially, the entry inside the inode or the entry inside the inode of the directory or the file that contains that entry of the directory points to the first. Well, such an approach of linked or the chain structure is good now in the sense we could accommodate large files and we would not have as much as metadata as we would have to store different pointers for each block in the inode structure itself. But well, this also does not quite solve our entire problem. In this case, we are able to utilize that bits and pieces of space that we have here and there throughout the disk, but so that it's good for sequential accesses, but bad for all others. Because if we do not have sequential access, then we would still have to parse through this whole linked list or this whole chain. And every time we parse through, we are incurring this additional overhead to get that the random access, like to get that data that is being randomly accessed. So quite still not there. Now, can you think of an hybrid mechanism now? A hybrid between an indexed structure and the chain structure. If you are thinking that, then yes, you are on the correct track. So we could have this mechanism where we have like a bit of indexed and then a bit of chained, a mechanism that combines advantage of both these approaches. And I would highly encourage you to think further and nail down the details of such an hybrid mechanism of how would that be working. So just to summarize the things that we have been discussing until now, let's take a look at this diagram where it's much neater than what I could draw. Well, not that my drawings are bad. My handwriting is very superb. Hardly you could understand everything, right? I know you have great handwriting understanding skills, so I trust you. Let's look at this neater, much neater diagram of the same example that we have been discussing. Here we have first block reserved for the super block. Then we have our bitmaps stored for these two. What are these? The bitmap is storing the allocation structures, right? And then these 5 blocks, what are they? They are storing inodes. So even in this diagram, we still don't have the blocks that stores the data. We just cannot fit it into the slide. And if we fit it, then we could not see or number those things. So something like this, we have mapped the space available on our disk with such a structure. So this is the close-up view of the metadata, the 8 blocks that are storing the metadata. Now, our inodes are storing different information as we discussed. And this is a particular example from ext2 file system. What contents does the inode of ext2 file system stores. So as we can see over here, the total size of how much this inode structure would need, it's not very large, as we discussed earlier. The information that it stores is very critical, and that's why it's the very important metadata. It stores things like, can this file be read, written, executed? So permissions of this file, owner of this file, how many bytes are in this file? So what is the file size? What time was this file last accessed? What time was this file created? When was it last modified? And so on and so forth. I'm sure you can read through the whole list, right? But all this information is very critical and very important. Then we talked about different ways in which our inode can give us a hint, like how can we map or how can we reach to our data from our inode, right? So one of the ways that we can store the content on the disk is by contiguous allocations, where we just store, which we called as extend based, where we just store the static block address of the file, and then we store the length of the file. So we know that if we want to access this file A, then we start from block ID 2 and we access 3 blocks after that. If you want to access the file called C, then we start from block ID 18 and then we access 8 consecutive blocks after that. The disadvantage of this mechanism is availability of consecutive free blocks. But the advantage is less amount of metadata to maintain. Such a mechanism of managing and maintaining data as contiguous in a contiguous chunk is being used by some of the popular today's file system, such as XFS and ext4. We talked about the chaining approach in order to resolve some of the disadvantage of that extent-based contiguous allocation approach. In the chaining approach, here I'm showing an example of file B. If we have a file B, we are storing the starting block and we are storing just the last block into our directory, which could be inode file or inode for a file or inode for the directory itself. Drop my pencil. So here, once we have the starting block address, we start reading that block, and the last entry in this block will be a pointer to where are we storing the next consecutive content of this file. And then so on and so forth, as we see here by this trail of blue marked blocks, we would be able to read the entire file. As soon as we hit the last block, we know that, hey, this is the last block from the entry that we are storing over here, so that we don't need to pointer chase anymore. We also talked about the multi-level index approach, where our inode stores information about pointers to the data blocks directly. And we could just reserve few of these pointers to point to the block of pointers itself. And thus it's called multi-level index. And this approach is also used by some of the popular file system of today, such as NetApp's Waffle, ext3, ext2, these file systems. Now, if we want to use, we briefly talked about that if we just rotate this figure like this, make it vertical, then what you would see is an imbalanced tree. Why to use an imbalanced tree like this? Why not a balanced tree? Well, something for you to think of. Finally, to summarize, which strategy to pick or how to develop a perfect strategy that works the best or gives us the best performance depends upon analyzing how actually our data is, right? If we have a data that needs very big size files, then well, we could come with one type of solution. If we have a data that has very small files, then we could propose another type of solution that could work best for that. But the key is, if we know more about our data, then we could anticipate that the observations that we built over decades by analyzing our data will apply to the data that we are seeing today. And if that applies, then the smart techniques that we design with these anticipations would be correct, would be better. So hoping that the things that we learn from history are applicable to improve our present with that hypothesis, we could learn that we see some particular characteristics when we look at different measurements done on file system. We see that most files are small. Average file size is growing slowly. Most bytes are stored in large files. So a few big files use most of the space of the disk. File systems contains lots of files. File systems are roughly half full. So even as disk grows, file system remains around 50% full. And directories are typically small. Many have few entries and most have 20 or fewer. So with these observations or notes into our pocket, now can we look back at those different designing techniques of how do we store the data or organize the data? And can you come up with a technique that you think would work the best? Well, that's your discussion topic of this module. So that's something that you need to compose your post on. Think of it, try to design an hybrid mechanism that could take advantage of multiple techniques that we discussed, ranging from multi-level index, chaining, contiguous allocations, all that, and see how you can take advantage of those different mechanisms to design a best file system for something, for the characteristics like this.